Okay, good evening, everybody. Welcome. Pierre's joined us and he's got his glass of wine so we can get going. All right. Thank you very much for attending. We're in for a very, very interesting talk this evening. Some of you may have seen the news flash about Earth having another moon. And then, of course, you get on social media the picture of two big moons close to Earth and all sorts of nonsense. Hennie actually developed his own, I think what you call it, ephemeris or whatever, and his own program software for other purposes. And then he fitted the trajectory of this moon and so on to his software. So he's going to tell you all about his software that he developed over the years, maybe a bit of his past history. I think you tell them. He's got a very interesting past history. And then also, about this whole mini-moon story, what the real story is, how it works, what happens, and so on. Okay, so over to you, Hennie. Thanks very much. We look forward to it.
Thank you. Okay, so a mini-moon called 2024 PT5, because it came by in 2024, traveled in the vicinity of the Earth from August 2024 to January 2025. So it's still close by, not completely gone yet. I plan to not only show you tonight what a mini moon was and is doing, but also to give you a feeling of the difficulties in simulating such event, in simulating the trajectory of this mini moon. I will sometime refer to the mini moon, another time to the asteroid, and sometimes to 2024 PT5 in my talk. They are all the same object. Okay. But let me just shrink my own importance to size. I was given the title Prof in the ad to this presentation. My real title is this long one, Emeritus Associate Professor. It may sound impressive, but it's actually of lower ranking than Prof for a number of reasons. Emeritus means I'm retired. This happened in 2019. Still working in the profession is better than having done it before. Associate means I could not quite make it up to a full professor in my 7 years at UCT. So doctor, in fact, is a better title, at least if it's far shorter. But the best is simply to call me Hennie. Okay, so having said that, let's just carry on. Okay, so this is some artificial intelligence generated info Google gave me on the mini moon. So let's just go through it. 2024 PT5 was a mini moon asteroid that temporarily orbited Earth from 29 September to 25 November in 2024. So that's now what AI is saying. Say again? Yeah, in 2024. The asteroid was about 33 feet wide, or about the length of a school bus. It was too small and dim to be seen with the naked eye or through amateur telescopes, but was observed with large research-grade telescopes. It followed a horseshoe-shaped path around Earth for about 2 months. Scientists suspect that it could be a large chunk of rock ejected from the moon's surface after an asteroid impact. It was first spotted in August 2024 by astronomers at Complutense University of Madrid using a powerful telescope in Sutherland, South Africa. So there is some nice local content. It broke free of Earth's influence on 25 November 2024 and resumed its regular orbit of the Sun. It's expected to pass by again in 2055. So info generated by artificial intelligence can be mostly true, but details can be wrong. For example, the mini moon was closest to the Earth on 8 August, which means the 29 September to 25 November that I mentioned here period in the slide is at least misleading. So just keep that in mind whenever you use AI to get certain answers. It's not necessarily all correct. My presentation tonight on the mini-moon is mainly based on a 3D dynamical simulation of our solar system, which I developed over many years, starting way back around about the year 2000. Why so many years? Although astronomy was part of a B.Sc degree I did at UNISA, I never worked in the field of astronomy, and it was and is simply an interest of mine. But dynamical simulations were very much part of my studying and working career in engineering. So at least the simulation part of my presentation has some proven merit. I made my investigation of the mini-moon perhaps more complicated than necessary, in that I started all my simulation runs, including the simulation of the mini-moon, on 1 January 2017. And not on 4 August 2024, when it was discovered. I used JPL Horizon's 1 January 27 info of the mini-moon, which is, of course, based on their simulation of where the mini-moon was at that point in time, because no one observed it then and there. Okay, so even that information that I got from JPL Horizons is based on their simulations of way back. The reasons for me to start my simulation on 1 January 2017 are quite simple. A solar system simulation must start at a given point in time where all the 3D speeds and positions of all planets must correctly be set. I've chosen 12 o'clock GMT 1 January 2017 as the starting point of all my simulations. I like running my simulations over a longer period because it is a better test of its accuracy than a short period of time. The better its accuracy for a longer history, the better its ability is to predict the future. Even in this presentation, if I show the results, for example, for the year 2024, the actual simulation run would have started on 1 January 2017, but the graphs are plotted only in the period I want to zoom in. Okay, so that's the basics of what I'm going to show you. So here are simulation results of the mini-moon trajectory published by the weathernetwork.com. And many trajectories found on the internet correspond with this. It's described as a simulation of 2024 PT5's orbit in a slow loop around Earth from August through December 2024. The yellow portion of the asteroid's loop indicates when it will be close enough to be considered a mini-moon or quasi-satellite of Earth. Now, 4 trajectories are shown on this slide. First up to 8 August, top left, then up to 29 September, top right, then up to 25 November, bottom left, and lastly up to 26 December, bottom right. But the research notes of the American Astronomical Society, AAS, by the researchers themselves, the first to officially publish on the mini-moon, have a different trajectory, different from this one. It also agrees with the JPL Horizons info, which is generally believed to be reliable. My simulation also agrees with the latter info, as I will show further on. So these are the trajectories according to the AAS research notes. But the most popular trajectory on the internet of the previous slide does not agree with it. It's quite different. The left trajectory is as seen from the top down on the ecliptical plane of our solar system, and the right one is as seen from the side of the ecliptical plane. The ecliptical plane, of course, is the plane in which the sun and the Earth travel. So I rotated these graphs through 180 degrees, that's why it's now they're upside down, to at least get the same orientation as the most popular internet trajectory shown before. But the correlation is still inadequate. I will next show a number of simulation results as generated then by my own solar system simulation, And in the end, they will agree with these graphs. So let's first of all look at the bigger picture. The mini-moon came in the close vicinity of the Earth because it has an orbit around the Sun very similar to the Earth's orbit. So it's not coming from nowhere. It's sort of traveling in the same type of orbit that the Earth has around the Sun. So here are the orbits of Mercury in cyan, Venus in purple, the asteroid, the mini-moon in white, and the Earth and our moon in orange and dark purple for 11 months from 1 January 2017 to 13 November 2017. I will mention a number of dates, but I always put them on the screen like that so you can know this is the period we're talking of for this slide. Although the Earth and asteroid orbits overlapped at the bottom right, they did not make a close bypass at the overlapping because they were almost at the opposites in the orbits in 2017. When the asteroid was here, the Earth at that stage, at that same time, and Moon were over there. And this was now in 2017. So no case of getting close to one another in 2017. So this simulation shows the results from 1 January 2024 to 31 December 2024, with the asteroid starting over here on that date, while the Earth was here, so quite close to one another. The asteroid chased the Earth and caught and interacted with the Earth down here, there where the overlapping is, causing its orbit to move wider than the Earth's orbit, as can be seen at the top. There's a difference there at the top between the white and the white orbit. So this happened in 2024, but not for many years before that time. And it will not happen again until around about 2055. The linearized parts, blue, are showing the JPL horizon's asteroid positions on 1 May, 1 June, and 1 July 2024. And thereafter, the asteroid positions were plotted every day. But the white orbit simulation was accurate enough that the blue orbit can't be seen below it after the linearized parts. In other words, on this scale, my simulation agreed very well with the JPL horizon's published positions of the mini-moon. This is the same run as before, but now from 1 January 2024 until 31st July 2025. A second linearized JPL horizon's asteroid part is shown on 31 January, 28 February, 31 March, 30 April, 31 May, 30 June, and 31 July 2025. Again, the white orbit shows my computer simulation to follow the JPL horizon's info very well on this scale. Okay, so this is the same run as before, but now over a longer period, here from 1 May 2023 until July 2026. Again, the white orbit shows the simulation to follow the JPL horizon's info. Later on, more detail will be shown, indicating that my simulation is good, but it's not perfect. So I will go into those details. It can be seen on this graph that the orbit of the asteroid will settle in a larger orbit than what it had before 2024. The smaller white orbit is before 2024, this one over there, and this larger one is the orbit after 2024. So before it was quite slightly smaller than the Earth's orbit, and now after 2024 it will be slightly bigger than the Earth's orbit. In this slide, I'm simply repeating the previous result, but the JPL horizon's positions of the asteroid is shown without the other objects close to its orbit. I do this to better show how parts of this published trajectory is linearized. I had to do the linearization to save me from inputting too much data in my simulation. Of course, only the corners of the linearized parts are accurate, agreeing with monthly data, but the smooth part was where daily positions were imported. In this plot, I'm showing the differences between my simulated positions and the JPL horizons positions of Venus, the Earth, and Jupiter after 7.5 years of simulating starting on 1 January 2017, before I started doing certain corrections. Ideally, the 2 dots for each planet. Can you see the 2 dots for each planet there? Is it not? Okay, later on I'll zoom in and then you will be able to see it. But okay, believe me, there are 2 dots for the Earth there, 2 dots for Venus, and 2 dots for Jupiter. And there should have been 1 dot. If my simulation and JPL should have agreed. So there's a small difference there. It looks like small differences, but when investigating, for example, the moon's orbit, the difference becomes significant. Now, the plus 0.2 degree and minus 3.0 degree written at the top of these graphs, perhaps you can read it, it's not very important, that you must be able to read it, are corrections I had to make relative to given JPL horizons info. I will explain them later on. Right now, I will explain another correction, namely to remove these differences, those 2 dots that are there instead of 1 only. So I will explain the correction I had to do to get that right. So this is the same result as before, showing the integrated correction I applied. It aligned the simulated positions with the JPL horizons positions very well. Now, only 1 dot can be seen for each of Jupiter, Venus, and the Earth. And so then I zoomed in a little bit. Now, I hope you can see the 2 there. And it's the same with Venus. So here are Venus and the Earth on a smaller scale before the integrated correction, and then after the integrated correction. So this is what I had to add to get the same results as JPL, at least then for the Venus and the Earth. But the moon relative to Earth will show the need for the correction even better. The JPL horizons, moon, and my simulated position of the moon differ by almost 90 degrees, as you can see there on this graph. This is now with the Earth there in the center. So it's quite a different phase of the moon that we will be seeing, looking at the one simulation and the other. And then again, if I do the integrator correction, the 2 moon positions relative to the Earth are quite the same. Okay, so now I will finally zoom into the asteroid trajectory close to the Earth. So now I will be able to check against what I've shown in the start of the AAS notes. Do I get the same result? So the piecewise linearized orange graph in the JPL horizons positions of the asteroid relative to Earth is plotted here from 1 May 2024 to 31 July 2025. And the white graph is the simulated positions of P5 relative to Earth plotted from 31 December 2023 to 31 July 2025. So there's an orange graph which is based on info from JPL horizons, simply imported into my simulation, and then they are the simulated results from my computer simulation, which is the white one. And the small circle in the center, if you can see it right there in the center, is the trajectory of our ordinary moon around the Earth. So it's quite smaller than this bigger sort of trajectory. I'll also zoom in a bit on that. Here it is more zoomed in. Okay, keep this picture now in mind, and now we go back to what was published. check the right graph from the AAS research notes with my results. They correspond quite well. I will also be able to produce the left graph by rotating my simulated 3D graph. Just go back, check this right one here with what I had before. It's quite the same sort of figure. Okay, and here it is more zoomed in. So now you can see the circle of the moon there even better. So next I'm going to rotate this image through 22.5 degrees about the x-axis. So the whole axis system is going to be rotated like this so that we can, because this is the ecliptical plane from the top. And we will also want to check what it's looking like if you look at the ecliptical plane from the side, because those are the two pictures that were given in the AAS notes. So here I rotated it through 22.5 degrees, then it looks like this, through 45 degrees, through 67.5 degrees, and then lastly from the side rotated through 90 degrees. Now again, compare this with the one there on the left-hand side, and you can see it's quite the same. Okay, so back to no rotation. Those of you who are very sharp would have, well, if your eyes are very sharp really, would have noticed that the top text changed from the indicated 1.002 times T del correction to integrated times 0.998 on this slide. On these results, both these corrections, one can either do in my simulation a time correction or an integrated correction. But on both these corrections, they do exactly the same thing. The results are not different. So I prefer the latter, rather change the integrator gain than the time, because for me it's more natural to do it like this. And so I'm not working here with relative time or anything like that, or relativity. So this is just a natural thing to do. So in the end, I went for the integrator correction rather than the time correction. So this is a repeat of the previous plot on 10 gigameter scales. In the following slides, I'll show you the effects of 3 corrections I had to make in my simulation. But first, this result is to show you that my simulation T del is small enough. If you do a time simulation, there's a time increment, which is very important. That's the number of times you'll repeat your simulation loop. It's determining that. And here it is half of the previous run, 100 seconds, T del instead of 200 seconds. But the result is exactly the same. So my recommendation, it's always a good procedure to check that the T del in a time simulation is small enough, like I did here. So it's small enough, it doesn't change. The result does not change if you make it even smaller. By the way, 200-second T del means that every calculation in my simulation of about 3,000 lines of code was repeated about 158,000 times for every year of simulation. And my longest simulation was over 39 years. So my computer had to do millions of calculations, just to give you a feeling of that. I previously referred to 2 corrections, one being a plus 0.2 degree true anomaly correction I had to make on the JPL horizon's position of the mini moon on 1 January 2017. And the other a minus 3.0 degree, which is a true anomaly correction I had to make on our own moon in my simulation at that same date. Now, the true anomaly is the angular position of an object in its orbit around the sun. This result is without the 0.2 degrees correction, the result that I'm showing you right now on the screen. Check the discrepancy in the white orbit on 1 May 2024, which is over there. You can see there's a jump there in the white simulation. After more than 7 years of simulating the trajectory. So you can see the 0.2 degree correction is necessary to take out that discrepancy. The effect of the minus 3.0 degree correction of the true anomaly of our own moon on 1 January 27 can't be seen on these graphs, on these scales, but it can be seen when moon rise and set times are checked. So I did do that sort of check to see that that is also the thing to do. So this is without the 0.2% integrated correction in my simulation. Again, there's a discrepancy in the white orbit on 1 May 2024, because there it's really, the simulation is coming down and then it's repeating itself. It's going back a bit. So there's overlapping there in that little circle. Also know that the latter part of the orbit is further away from the JPL horizon's positions than on the previous slide. Okay, so now here's a big difference. If you now compare the previous sort of picture, that figure with this one there, look at the white orbit. So this was done with my simulation, but without the precise JPL horizon settings of the positions and velocities of the mini-moon, the Earth and the Moon on 1 May 2024. So I had to do corrections quite close to the real approaching date of the object. Although no discrepancy in the white orbit can be seen here, over there, which is the 1 May 2024 point, meaning that the trajectory is correct up to that point. The 3D speeds of the mini-moon must be set correctly. So this thing is very sensitive, the whole trajectory, very sensitive for exactly the right positions. Not only the positions, really the speeds. The three-dimensional speeds must also be correct. Otherwise, the remainder of the trajectory is significantly wrong. So the resetting of the positions and velocities must be done because this graph is significantly different from the previous one. All of these required simulations, corrections clearly demonstrate the sensitivity of the asteroid's trajectory with 3D positions and velocities at the correct time. To summarize, here are all the corrections I had to make. A plus 0.2 degree adjustment on the true anomaly of the mini-moon on 1 January 2017, when every simulation of mine started. A minus 3.0 degree adjustment on the true anomaly of the ordinary moon on 1 January 2017, and a minus 0.2% integrator gain change on every integrator used in my simulation. I use a rather simple bilinear integrator algorithm, whereas the AAS researchers used a more sophisticated algorithm. So perhaps that's a reasonable reason why I had to do this gain correction to get the positions in the end correct. A resetting of the 3D positions and velocities of the mini-moon, our own moon, and the Earth on 1 May 2024, shortly before the mini-moon was first observed in August 24, had to be done. The velocity seemed to be the major factor here. Okay, so this is my last slide, and it runs up to the year 2056. The red graph is the distance of the asteroid from the Earth over all these years. The red graph dips indicate the closest the mini-moon was to the Earth, over there. And when in future it would be close again, over there. And well, apparently they're not so close as now. So don't worry if you're still here in 2055, not a big danger here. You will be what? Over 100 years? Yeah, I think I will be 101. Okay, so the first date was 8 August 2024, and the return date will be on 25 December 2055, according to my simulation. It agrees with the published expected return year of the asteroid rock. Okay, but all Christians know there is another infinitely more important rock returning soon. May we all be ready for his coming, though we don't know when that will be. I thank you all for your time.
KPL predicted further out.
Do they also do predictions?
That prediction was only from the September. Why didn't they predict it further out?
Yeah, no, they
Before.
yeah, no, they predicted all the way. So that's why I got this 2017 data, for example, then it's way back, but they also predicted for the future. I didn't go and check exactly what they say about this 2055, but that's the most sort of common sort of date you find on the internet. So I can go and check it against the JPL themselves, what they say, or perhaps the research notes that the researchers gave out will. But if I remember correctly, they also said 2055. So I was happy with my simulation, even in terms of the future, is more or less correct. But yeah, JPL horizon should be more accurate than I am, because my simulation is running with 12 objects in our solar systems. They have like 18 or 30 or something like that, many more objects in their whole solar system simulation. So they will be more accurate than I am, but I'm more or less right because of the 2055. Yes.
Why did you choose this particular object for your simulation rather than any other objects that might be often tripped by?
Oh, simply because this one came by now in 2024, and we read about it on on the internet and on the media and so forth. And I do check my simulations also with other stuff like the super moons and all of that. So I've done that before. So I can take like 12 objects in my solar simulation, and the 12th object can be anything. So that's why I just decided, okay, let's just try it. And because the notes came out with this sort of particular orbit or trajectory, the trajectory around the Earth, I thought, that would be a very nice way of checking the accuracy of my simulation. Can I get it? Whereas if you do check the sunrise and the super moon and so forth, I know in that sort of accuracy I'm okay. But I was not sure how accurate I would be when looking at a detailed sort of trajectory like this one. So that was really the reason. And all these corrections I had to do, that was never necessary before. So I learned a lot from doing this detailed thing. And I definitely would like to find out why is it necessary for me to put in that, especially the integrated gain correction, to get the same results as JPL. There must be a reason for that. Because
share your simulation with the JPL.
yeah, I can send. Yes, I can. I will be willing if they would be interested in seeing it. I'm not sure. Perhaps they will someday tell me I must use a better integrated algorithm. Perhaps they will just simply say that. But so yeah, but I'm willing to share. Yeah, no problem.
When you say your simulation, 12 solar system objects,
Yeah.
are you calculating details of all the 12 objects?
Yeah.
So that's a 12 body problem.
That's right. That's right.
It's non-trivial.
Yeah, no, you can't do it without a simulation. You can't mathematically figure it out, or get a result. Yeah. Yeah, so each object of the 12 will have an effect of each other object. So if I send in a rock like this into the system, Jupiter, Saturn, every one of the other planets will have an effect on its trajectory, though very small. but everything is calculated at every point in time, the forces of each one on the other. Simply in terms of, no.
That's a 13th one.
Well, but I mean, I can put in planet X in the place of the minimum. There I can put in anything. For example, what I've done before is to make in another simulation is to let a very, very big sort of almost the sun come through our solar system. And if you choose that right correctly, you can see it's all sorts of funny things. We go completely in another orbit, the Earth. We can lose our moon. So you must choose it quite nice to see that sort of effect. But my simulation can do anything like that.
Oh. Has this mini-moon, this asteroid been observed before?
No.
So, but it could have been visiting
Yes.
in previous.
Yeah, no. I think around about every 40, 50 years, if we look at this 2017 to 2055, more or less, that sort of time, it will always be close to the Earth, but it has never been seen before. But it's not the only one. There are other rocks also doing the same thing. So I think the sort of standard model is that, yes, it has been there for many, many times. But now, this time around, it's the first time that it has been observed.
It's an elliptical orbit.
No, it's quite similar to the Earth's orbit. As I've shown there in those graphs in the beginning, yeah. No, it's so normal elliptical with its parameters specifying. Yes.
The solar system is controlled by the gravitational field from the sun. We all know that.
Okay.
And the moon is controlled by the Earth's gravitational field.
Yeah.
What controls many of the moon? Is it the moon has any influence from the Earth or from the sun for that matter?
From all of them. It will be influenced by every planet in the solar system and by the sun and by the moon. All of that will have an effect. I mean, every object in the solar system, there will be gravitational forces between them.
It's compensated.
Yeah. So that will always be there, and it's part of the simulations to calculate that, and then this will be the end. So one cannot really talk of only controlled by the gravitational force of the sun. It's whatever object is in there will have a gravitational force on every other object.
Is aware of the existence of many birds?
When I say again?
When is aware of the existence of many birds?
I was only aware when I read about it in August or September or so, when it came out on the media. But it was discovered the first time, I think I've said, on the 4th of August 2024. That was the first time it was really seen. Okay, question there at back, please. It's far too small. Yeah, no, it's far too small. No, I don't think there will be anything there. I'll go back to my thing.
Very quickly, just take one loop around this metal.
No. It's this sort of horse-shaped thing that you see there. It didn't go really around the moon. It came down like this. It did this sort of thing, and then it went back. But it also moved in the other axis. That's why when I rotated the axis system, you can see it didn't just do that simple thing. It also went down while doing that. But it's here for about 2 months, and then it will go again on its way back on its normal trajectory around the sun. Just
Typically, how close did that mini moon get to Earth in terms of kilometers?
okay. This picture of mine, I will try to read it. that scale there is 1 gigameter. So this is more or less 0.6 gigameters from the Earth. That is the closest that it was to the Earth. 0.6 gigameters. So you must now convert gigameters to the power to the kilometers. Multiply with 10 to the power. Gigameter is 9. 0.6 gigameters, and 1 gigameter is 10 to the power no, 9, I think. We can make sure of that, but 600,000 kilometers. Yes, I think that's the answer. Yeah. No, it didn't hit us. Well, you can't say it can never hit us. If the trajectory is different, it can hit us, but it was quite close there, and the expectancy that it will be not as close in the future. So.
600,000 is still double the distance from the.
Yeah. Just over there.
Can you use your simulation program to calculate the profit value?
In principle, I can. I haven't yet put in anything that is launched really from an object going away. It's possible to do, and that can become my sort of 12 object. But so it's possible, but I haven't done that yet. Yeah.
Well, two questions then. The one is, I get what you say, that it moved out of the planetary plane, but above and below our normal planet.
Yeah.
Where did it come from and where has it gone? Has it gone to the asteroid belt?
Okay, some people say it's coming from the asteroid belt. I didn't really go and read up what everyone is saying about that. Some is saying that. The sort of AI info that I shown in the beginning said it came from an asteroid that hit the moon, and the chunk of rock was thrown from the moon, and that's where it's coming from. I think that's fairly unlikely, but that's what some people are saying. So I don't know if you've got a better idea of where it was coming from. Or...
I think it would be more asteroid-like.
Yes.
Disturbed somewhat time in the past by an object moving past the asteroid belt and then captured and orbit around the sun.
Yeah.
I think it's asteroid forward.
Yeah.
It seems to be, broadly speaking, in the same orbit as the Earth.
Exactly.
Very different speed to the Earth.
That's right. So that's why it's, and then eventually it will catch up. If it's going around the sun for enough time, then it will catch up, and then it comes close to.
Much faster to stay at that distance from the sun because it's so much lighter than the Earth.
Say that again.
For it to maintain the same orbit more or less as the Earth,
Yeah.
it has to be going at a much faster rate because the mass is much more than the Earth before it being a stable distance from the sun.
No, you can, if one looks at these calculations on everything, you can get different masses, same orbit. You don't.
They have different masses, but they can't be the same speed.
No, they can be the same.
Decay.
It might decay over a long time, but in principle, it can have basically the same orbit. It's not dependent on the mass. Yeah, and that's exactly what's happening here. It will stay in that orbit, which is quite the same as the Earth, although it's much smaller than the Earth.
What is specific proximity to the Earth? Did the velocity increase or decrease?
I think it would have increased and then do its little thing and then decreased again. So
account then for its new orbits being slightly larger than the orbit prior.
yeah, that is the sort of thing that will happen. And the other thing is, if it comes very close to the Earth, you can even get that is going away from the Earth in completely a different direction. So you can get a a thing, yeah, what do they call that? That sort of thing that sort of thing can happen, but then it will have to be much closer to the Earth than what it was here.
How many of these things do we not see? How many more are there?
I think thousands, thousands of objects. Yeah.
Very much. Any more questions? No more questions. I'd like to present a gift from the Modern Astronomy to the speaker. See, Peter has got it wrapped up in brown paper so you can't see how expensive it is.
Thank you.
Thank you very much. Good talk.
Okay.
Thank you very much.
Okay.